Okay.
Hello, everyone. Thank you for joining the Geoscience and Geoenergy webinar on 17th of March 2022. I'm Christine Meyer, a postdoctoral researcher at Unicamp in Brazil. Hadi was not able to join us today, so I'm pleased to co-host the webinar together with Sebastian Geiger from TU Delft in his place. It is pretty much the second anniversary of the first lockdown back in 2021, amid the idea of this amazing and successful webinar was born. For all our regular guests, we are grateful to you all for supporting this initiative for nearly 2 years now. But if you are new here and haven't subscribed to our YouTube channel yet, please do this to access all the past lectures and to get notification of the upcoming ones. So today, at our 95th lecture of this webinar, we are pleased to welcome Marco Dentz as our keynote speaker. Marco has been a professor at the CSIC in Barcelona, Spain since 2009. His research focuses on hydrodynamic flow and transport in porous and fractured media. He received a doctoral honours in physics from Heidelberg University in 2000. He was a Minerva Fellow at the Weizmann Institute of Science before he joined the Technical University of Catalonia in Barcelona in 2003, where he was a Ramon y Cajal Fellow. He was awarded the consolidated grant of the European Research Council in 2013. In 2021, he was awarded the Interpor Medal for porous media research, and today he will talk about flow and transport upscaling from the pore to the regional scale. It is our pleasure to host you, Marco, this week. To the audience, please note his lecture will last for about 30 minutes, followed by questions and discussions. Like always, type your question in the chat box and Sebastian will go through them and share the session afterwards. Feel free to type your question at any time during the talk, as this might trigger further questions from the audience. And now, Marco, the floor is yours.
Thank you very much, Christine, for the introduction. And thanks to Hadi, Sebastian, and you for organizing these seminars and also for inviting me to give today's seminar. I'm going to talk about flow and transport upscaling from pore to regional scale. So I'm talking about passive flow and transport, now reactive flow, and now flow still have a feedback with transport, for example. It's just passive transport.
Marco, just sorry for interrupting. Yeah. Do you mind just switching your microphones again, because we get a lot of static?
Okay, one moment. So it's better with the AirPod speaker, maybe. Better?
That's better, yes.
Yes.
Yeah, that's much better. Super.
Okay, excellent. Yeah. Super, what I said before, so thank you to you, Sebastian, Christina, and Hadi for organizing these seminars and for inviting me to today's seminar. And I'm going to talk today about flow and transport upscaling from pore to regional scale. And I would like to acknowledge people who have worked with me in the last years on different topics related to this general theme, which are Alexandre Puguiro, Alessandro Comolli, Vivian Hakun, and Juan Hidalgo at the CSIC. And then Tanguy Lebonne from University of Rennes, Philippe Bous from University of Montpellier, Jeffrey Hyman from Los Alamos National Lab, Peter Kang, who is now in Minnesota, Veronica Morales, UC Davis, Markus Holzer, Matthias Willmann from ETH Zurich, Arash Masoudier from Catholic University of America, and Matteo Icat from University of Nottingham. This is the outline of my talk for the next, hopefully, 30 minutes. So first I'm going to talk a little bit about flow and transport and porous media. So I'm going to talk about passive transport. Then about upscaling in a Fichtean dispersion paradigm. Then I'm going to talk about observations and evidence of non-Fichtean transport, and then how one can upscale this. And then I will give some examples for the upscaling from pore to regional scale. So first, flow and transport and porous media. So porous media are in general heterogeneous. So this is what makes the whole thing interesting, as we'll see in a few minutes. So the type of scales we are considering is say micrometer to millimeter scale. It would be the pore scale, where here we have a barrier sandstone image, and this would be the way we represent this computationally. This is a digitized rock sample from an X-ray microtomography image. So this is say gravel sand material that gives rise to different hydraulic conductivities, and here we use, let's say, the standard model of hydrogeology to represent this in terms of a multi-Gaussian hydraulic conductivity field. And then we have also fractured media that we represent in terms of discrete fracture networks, where there can also exist an interaction with the matrix. The complexity in porous media transport comes from the structure, because the equations are relatively simple. For flow, for example, we have the Stokes equation on the pore scale. So we are only considering laminar flows with low Reynolds numbers, and we can have a relatively complex pore scale. This is actually a relatively simple one here. It's just a type of granular medium. But what we see is that we can have a broad distribution of flow velocities, what you see in different colors, different magnitudes of the flow velocity. And to the right, we have how transport of a solute that is initially distributed along a line looks like. So we have a quite heterogeneous concentration field. And similar things we observe in the Darcy scale, where we have different flow velocities because we have different hydraulic conductivities. And also here, the transport looks relatively complex. So we know the equations to describe this type of behaviors, which is the advection dispersion equation for the concentration, where we have U of x, which is the heterogeneous flow field, either given by Stokes or by Darcy equation, and we have a diffusion or dispersion tensor. In the following, we are going to look a lot into transport in terms of particles. So the transport of particles that constitute, let's say, a concentration distribution or concentration distribution can be considered as the density of particles that are transported according to this advection and diffusion equation. So the position of a particle changes because of advection in the flow field, plus this random force, which represents diffusion or dispersion. Now you could say, okay, if we know how the detailed transport looks like, why should we do upscaling? The reason is there is a computational requirement, because we are typically not able to represent so much information as we need in order to resolve all the smallest scales. So there's a characterization problem. I mean, if I want to solve transport on a regional scale, I cannot resolve this medium structure, for example, on the pore scale. No? It's like when you want to describe diffusion of a substance, and you say, okay, I'm going to characterize it based on the molecular interactions between atoms or molecules. And another thing is, of course, I want to have physical understanding. Now, if I observe something on the large scale, I want to understand why it is happening, and not say, okay, I have 1 million degrees of freedom, and this is what comes out. So now upscaling.
Sorry, Marco, for interrupting you once again. We still keep getting quite a bit of interference. So maybe the airports need to be switched off at all.
Okay.
Apologies to the audience.
Okay, let's do it.
It's too nice of a talk for having the interference in the background.
Okay, right. Is it now better?
Now it's better again. Yes.
Okay, good. So now the first thing I want to, yes?
Thank you very much.
No, I'm sorry for this trouble. So first we talk about hydrodynamic dispersion. No? So so what you see here on the left, this is some results from a tracer experiment that was conducted in a moderately heterogeneous medium on the field scale. What one observes here for conservative tracers, this bromide, is that as the bloom is transporting through the medium, so we see a significant longitudinal dispersion of the bloom, which cannot be explained by pore scale dispersion or by diffusion effects. In fact, when one looks at different experiments on different spatial scales, one sees that the longitudinal dispersivity is actually increasing with the scale. So this is data that was compiled by Geller et al. So now how can one quantify this scale effect? So the idea, that is a relatively simple idea that I'm going to describe here, is to consider, if we are in this particle picture, to consider the particle trajectory and say it is a particle moves in the mean flow plus some fluctuations about the mean, just the velocity fluctuations in a heterogeneous flow field. And then I can define a dispersion coefficient by essentially integrating over these velocity correlations. So this is what dispersion is about. Now I have velocity fluctuations. Some particles go faster, some go slower, and this is causing a dispersing of a plume. And so now this dispersion coefficient I can describe as consisting of the variance of velocity times a correlation time, a characteristic correlation time. An assumption that we have in this picture is that the velocities, particle velocities, if I consider a velocity series in time, that they evolve on a characteristic time scale. So I can clearly assign a time scale, and if I'm at times that are very large compared to this correlation time, the signal looks basically uncorrelated. So I can model it as a Gaussian white noise with a certain covariance, which is just given by the dispersion coefficient. So now if I have scale separation, meaning that I have observation times that are much, much larger than this correlation time, I can write down again an advection dispersion equation for the concentration or distribution of particles, or the concentration of a solute, where I just have now an advection by the mean velocity and dispersion by a dispersion tensor. What one wants is predictability, which means I have now a large scale and upscale transport model, and I need to be able to relate it to medium and flow properties. So when we look from at the upscaling from pore to laboratory scale, which would be hydrodynamic dispersion, we can readily come up with an estimate for this hydrodynamic dispersion coefficient by just looking what is the characteristic correlation time for velocity. It's just the pore length divided by a mean velocity, and the velocity variance is always proportional to the mean velocity squared. So if I use this formula from the previous slide, I get an estimate. Hydrodynamic dispersion is just mean velocity times pore length. No? Then when we go from Darcy to field scale, it's very similar. On the field scale, I have a characteristic correlation time, which is the correlation length of hydraulic conductivity or log hydraulic conductivity divided by a mean. The velocity variance one obtains from perturbation theories, the mean velocity squared times the variance of the log conductivity. And again, I get an estimate for macro dispersion in this case, which is the log K variance times mean velocity times pore length. And now this is a very nice situation, no? Because we have an upscale transport model and we can fully parameterize it just in terms of the hydrodynamics of the problem, the mean velocity, and some geometric characteristics or medium characteristics, namely the characteristic length scale and the variance. And then we can use this model to make predictions for transport, for example, for spatial distributions. If we start from a point source, spatial distributions say look Gaussian, so there are ellipses if we have different dispersion coefficients in longitudinal transport direction. And when we look at breakthrough curves, we get this type of shape. For the breakthrough curve, we have a clearly visible maximum concentration, and then we have an exponential decrease for longer times. This is described by an inverse Gaussian distribution. So now a quick recap. So when we do this type of, let's say, Fichtean upscaling, we require that particle velocities should decorrelate on a clearly defined time scale, which should be much smaller than our observation time. And then we can describe particle velocities as a temporal Markov process. This is what we have done with this simple advection equation. And then we've seen that this is a very general principle. It's valid across different scales, and we can make predictions on dispersion coefficients from pore to Darcy and from Darcy to regional scale. However, when we look at other experiments in more heterogeneous porous media, we see that this does not work. So here, these are tracer plumes from the MADE side, from the MADE experiment, which is called macro dispersion experiment, which was conducted in the end 80s, in order to test again the macro dispersion theory of Geller, Dagan, and other people. And it turned out that it didn't work. So this is a solute plume that evolved from a more or less, let's say, instantaneous point injection. Of course, instantaneous means injection over a few hours. But what it looks like is a steady state plume, for example. You know? So it's not, there is not a Gaussian clearly moving along downstream. And similarly, when we look at the spatial variance, we don't see a clearly linear increase of dispersion. So now I'm going to show some numerical examples here from numerical simulation in this barrier sandstone sample, when we solve Stokes equation and particle tracking. And when we look at breakthrough curve, we see that we see two things. Number one, we do not have these exponential tails that we saw a few slides before, but power tails. And secondly, we see that we have a dependence on the injection condition. So whether we inject flux weighted, so the number of particles depends on the velocity at the injection plane, or uniform, so we get different slopes. So there is a lot of memory present. And when we look at velocity series, velocity time series, we see that they look very different from the ones that we need for Fickin description. Also here we see an intermittent signal. We have high velocities that fluctuate relatively fast and low velocities that hardly fluctuate. Yeah? And of course, we have particles that are retained in low velocities for a long time, and this is what is causing these long tails, and what is calling memory effects. We see the same thing on the Darcy scale. So these are numerical simulations in this type of multi-Gaussian K-field for variances at around 6 or 7. And again, we see memory effects, we see dependence on the injection conditions, and we see strong tailing, both in the breakthrough curves and in the spatial distributions. And again, velocity time series, they show this intermittent behavior. No? Particles are retained in low velocities and fluctuate relatively fast when they go into high velocities along a streamline. And in discrete fraction networks, we have the same behavior. Breakthrough curves, again, depend on the injection condition and show very strong tailing. Similar, and we have a similar phenomenology for the particle velocities, again, intermittency, and memory effects because of retention in low velocities. So a quick recap. Again, remember, Fickin transport requires that we have scale separation and so that observation times are much larger than a characteristic correlation time scale. But this seems not to be valid in general, because so what we have seen now is that transport timescales seem to be very broadly distributed, and this means on relevant observation times we cannot use a Markov process, because the processes do not decorrelate on the timescales that we are interested in. Now the question that we have is there another principle that we can use or that is valid across scales, like this Fickin paradigm. So now we come to our upscaling concept. So we have seen that we have intermittency in the velocity signals when we look at velocity signals in time. No? And the reason is that, as I mentioned a few times, particles are retained for a long time in low velocities. But now if we say we sample instead of isochronically, no, in equidistant time, we would sample velocities equidistantly in space. This is what you see here. This is a trajectory, and we just sample in equidistant distances. Then, of course, we go into a different way of describing transport. Now, the first way, isochron sampling, corresponds to a random walk type of description that we are used to. So I'm moving a particle according to the velocity in a certain time delta t. If we take this second way of describing transport, then we would go into a continuous time or time domain random walk picture where I move particles a constant distance, and then the time that I move is variable according to the velocity that I have within a certain element delta S. So now when we analyze particle velocities isochron, again we have this strongly intermittent behavior, but when we analyze them equidistantly, we see a relatively, let's say, regular random signal. No? And we see that velocities, they actually change on a constant, on one single constant scale. The same we see on the Darcy scale. Again, here we have intermittent signal sampling in time and sampling in space, let's say relatively regular, and the same also for DFNs. So what we see is that velocities, they change when we go from one fracture plane to the next. So the different shadings are different fracture planes. So now, quick recap. So we have intermittency, which means transport timescales are broadly distributed. And this means particle velocities cannot describe a Markov process. So we have memory effects because particles can stay in the same velocity for a long time. So this means they remember their velocity for a long time. But what we have seen is that speeds, they rather evolve on a characteristic length scale than a characteristic time scale. And when we do equidistant sampling, we remove this memory. And now we can put these insights in a mathematical model, in an upscale transport model, where we say, okay, we consider our particle velocities now as Markov models, but evolving in space instead of time. So it's a kind of a spatial Markov model. So I'm moving along a streamline, a certain distance delta S, and I'm changing the velocity according to some prescription. Now the stationary velocity distribution that I need to parameterize the Markov model is given simply instead of the flux in terms of the flux-weighted Eulerian velocity distribution. So if we do isochronic sampling, let's say the steady state distribution of particles would be the Eulerian PDF. This is a direct consequence of volume conservation, if you want, and you can derive this using the Reynolds theorem. And but in our case, we do equidistant sampling, so we get a flux weighting. Then we have the Duke theorem, which says that if I have a Markov process that is both stationary and Gaussian, it is necessarily an OU, non-Stein-Uhlenbeck process. So what we do is now we transform velocities to a normal random variable, and then we advance this normal random variable according to a non-Stein-Uhlenbeck process. So all of this put together gives an evolution equation for the joint distribution of particle position and particle velocities. It's a type of a simple Boltzmann equation, where this distribution evolves in space according to the current velocity of a particle. And here on the right side, we have transition probabilities that tell us the velocity changes of the particle between transitions. So now, if the correlation scale is much smaller than the observation scale, this is what the situations we are typically interested in now when we do upscaling, then the particles are statistically equal, at least in space, because now we have chosen to take this point of view of spatial motion, let's say. Then we can describe everything by a, let's say, normal continuous time random walk, where we have velocities that are independent between steps. Now, because now I take such a long step that I don't have memory before, so I have a simpler Markov model, and then we end up with an evolution equation for the concentration or the particle density, which is simply a non-local equation in time. Now I have two memory terms that account for these memory effects in velocity and in dispersion. So now what we have seen is that, okay, Lagrangian speeds, particle speeds, they can be described as Markov processes in space. Then we have used an Einstein-Uhlenbeck process to propagate the particle speeds. And it looks like that these principles are valid across scales, similar to what we have seen before for the Fickian upscaling. And we can also parameterize this model, namely in terms of the Eulerian speed distribution. Then we have to identify a correlation scale, which is typically of the order of on the pore scale, the pore length, on the Darcy scale, the correlation lengths of flock hydraulic conductivity, and for discrete fraction networks is of the order of the average fracture length. And then we have to specify also an advective tortuosity, because we are describing particle motion along streamlines, which are typically tortuous. So this means that they are longer than the linear distance. So now I want to give you some examples where we use this framework to do upscaling from the pore to the Darcy scale. So here we have this example for Berea sandstone, where we measured the Eulerian speed PDF. And what you see is that we have here very high, typically high probabilities for very low velocities. And this, of course, is having a large impact on transport. Because we can get a lot of retention. And so when we look at the breakthrough curves, you see here, so breakthrough curves for fluctuating uniform injection. You see the symbols are the results of the direct simulations, and the lines are the results of this continuous time random walk model that we can parameterize in terms of the Eulerian speed PDF, and that we can condition on the injection conditions. And you see that it gives relatively well. It describes relatively well the numerical data. Similarly, for the Darcy scale, to go from Darcy to regional scale, we have here a log normal K distribution, which gives rise to more or less, let's say, skewed log normal distribution for the Eulerian speed PDF. And here again, you see the symbols is the numerical data of these direct simulations, and the lines, which you can here see not so well, are let's say the predictions of the continuous time random walk model. And here the same thing for spatial distributions. And again, the same for discrete fraction networks. We have used the same modeling framework, the same model, just parameterized it differently with the speed distributions from the discrete fraction network, and we get very, very good descriptions of the numerical data, again, for different injection conditions. So then we had used this model also to model the transversely integrated blooms of the MADE-1 tracer experiment. That's what I showed a few slides before, which was, so this experiment motivated a lot of studies on non-Fichtean transport. And so what we did is we took hydraulic conductivity data from the literature. In this case, we solved then the flow equation. Of course, we had to numerically solve the Darcy equation in order to do the flow statistics. So here you see I think this is the hydraulic conductivity distribution, and this is the velocity distribution that we got. And then we parameterized the model in order to describe the vertically and horizontally integrated concentration blooms. And what we obtained, so you see at the crosses is the experimental data, and the lines is the CDRW model. It's relatively well described. And with this, I come to the conclusions. Conclusions are Lagrangian speeds evolve as Markov processes on characteristic scales. But this is clear when we look at transport in porous media or in steady velocity fields. There is always, let's say, a characteristic length scale, unless we look at media that have some kind of a fractal structure. But otherwise, processes occur on given length scale rather than on given time scale. Now, all the time scales are determined by velocities, and let's say when we look at hydrodynamic transport, time scales are determined by a velocity and by a characteristic length scale. And we can describe the evolution in terms, in this case, of an Ornstein-Uhlenbeck process for the normal scores. This seems to be a universal principle that we can apply across different scales. And then the upscale transport model can be, in fact, parameterized by flow and medium properties. There are still some open questions, but it is possible to use, let's say, non-transport attributes in order to parameterize the model. This is very important. And we can write down the random walk model. It can be implemented numerically relatively easily. So one can have, let's say, a transport simulator, a large-scale transport simulator that is relatively simple. And some implications in Outlook. So one can also modify this type of transport framework for different type of transport situations, for example, for dispersion of colloids, of active particles, bacteria. One can look at dispersion under unsaturated multiphase flow conditions, because what we need is we need a flow field, no? And we need some geometrical information. In principle, we can parameterize a flow model, and can also adapt it to look at fluid deformation and mixing, and can be used to also look at chemical reactions and mass transfer between flowing and non-flowing regions, like mobile, immobile situations. Some things that are not clear, in principle are still open questions, is what is the relation between the Eulerian velocity distribution and the medium structure? So this is a question that one can answer for specific situations. For example, for stratified flow fields, it's clear how to do this, or for flow fields in inclusion media, but otherwise, oftentimes it's not known. But this we need, of course, as an impact for the model. Also, unsteady flow is something that still needs to be done. And everything that I talked about today is for purely advective transport. So we have not talked about how to take into account diffusion or local scale dispersion. This changes, of course, the way particles sample the velocity field. And also multidimensional transport, there are a few works, but in principle, this is still a relatively open question. Thank you very much. That's it.
Thank you very much, Marco, for a really nice talk, and brings me back to some work I've tried, by no means as eloquently as you, to do a decade or more ago. So I have quite a few questions by myself related to your talk. Let's start with some of the audience questions here. We have one from Arvind Kumar. Thank you for this talk. When we talk about breakthrough curves, we talk about mixing or spreading of traces in the flow. Can you give a physical picture of breakthrough curves in simple terms?
Yeah, so here I'm really talking about spreading. Yeah, we are not talking about mixing. So we considered here purely advective transport. And for example, when we look at the discrete fraction network, we were injecting particles along an inlet plane, and then we recorded when particles arrive at a control plane within the medium or at a control plane at the outlet. So this is quantifying purely spreading of the plume.
And thank you. And Arvind has a follow-up question. You ask, what is the reason behind the appearance of fluctuations in the breakthrough curves? What role does the Reynolds number play in breakthrough curves if flow is unsteady?
So the moment we have considered only low Reynolds number, so it's just laminar flow. We do not consider any let's say inertia effects, or we don't get temporal fluctuations of the flow. So it's only laminar low Reynolds numbers flows. So I think you referred to fluctuations in the breakthrough curves. So these fluctuations in the breakthrough curves, they come from the fact that we consider a finite sample. No? So we have a finite medium. Of course, there are fluctuations. So we have an infinitely big injection plane, and we are considering one realization of a discrete fraction networks. So there are fluctuations. On one hand, because of the medium structure itself, and also because of the number of particles that we use in order to determine the breakthrough curves.
Thank you. One question is similar to one that crossed my mind, is from Raphael March, and he wonders, is it possible to extend your model to multiphase flow? Is there anything you can, what direction do we need to go to do this? I remember, again, a decade ago when I talked to Brian Berkowitz, so the was one of the masterminds behind the continuous time random walk theory. He always said you need to have the steady state flow field. In multiphase flow, your velocities, your phase velocities are changing. Has that field moved forward? How do we tackle that that extension?
So for multiphase flow, I mean, we can talk about two things. No? I mean, one is the transport in multiphase flow. This would be one thing, or the other thing is the transport of a saturation field, no? Of saturation in multiphase flow. So for let's say solute transport in multiphase flow, I mean, if the flow field is steady, and we can have situations for this. Now, for example, when we look at unsaturated flow, there are situations that you can have a steady flow field if you maintain an overall saturation, so you have a steady state flow field, and there you can use the continuous and random mode model as well as for this type of situations that I have shown today in order to make predictions on transport. When we look at let's say multiphase flow, I want to describe the saturation or the fluid saturation. Then I remember some works by Patrick Jenny and Patrick Jenny's group, and what they did is they wrote down, if I remember correctly, multiphase flow problem in terms of a random walk particle tracking formulation. No, because so you can imagine you have your saturation equation, which resembles somehow a nonlinear advection diffusion equation. No, you have an advection term that depends on the saturation. Your dispersion coefficient depends on the saturation, and then you can write this down as a Langermann equation if you want. But you have to, I mean, you have a feedback now. So you have your particle equation, then you have to convert this to saturations, and you have to recalculate the flow field. But in principle, at the moment, you can write something down in terms of particles, and something similar has been done, I think, by the group of Erwin Zehe in Karlsruhe as well for unsaturated flow. I think if you are able to, as I just mentioned, we're able to write down a random walk equation for your quantity of interest. In principle, it would also be possible to extend this to continuous and random walk situation. And this was a very long answer. I'm sorry.
No, that's fine. It's nice to see that there's so much work still to be done. We do have a question from a user, the Holocene. He says, hello, is there any significant difference we do upscaling conventional, so classic type reservoirs, and unconventional, very tight reservoirs? So can you use your approach in both cases?
Yes, when we look at solute transport, let's say in principle, what we need for the upscaling is we need velocity field and we need characteristic length scale. And then something that I did not emphasize maybe enough is another thing that we need is we really need some kind of randomness in the system. Now we need a medium that is sufficiently heterogeneous and random, such that when I look at particle transport, for example, that a particle as it moves through the medium can sample enough velocities, even enough different velocities. This is something which is not given in stratified media, for example. That we do not have this type of ergodic situation. But in principle, let's say whether you have a tight reservoir or not, this framework works depending on, is it sufficiently heterogeneous? I have a steady velocity field, and I can identify a characteristic length scale.
But for very tight formations, say shale formation, wouldn't then also be the diffusion part, the mass transfer between the mobile and immobile domains not become more important?
Exactly, not super. Yes, I didn't think about this, but this is true. Yes, of course, and this we can include in this modeling framework. So I've not included this in the today's talk, but for example, for these fraction networks, the way we model mass exchange between fractures and the matrix is that we add basically an extra retention time to this kinematic advection time. So we treat this mass transfer process as, it's a very technical term, as a compound Poisson process, which means we have a certain rate. Now I say my transport along a fracture takes, let's say, 10 seconds, well, or 10 hours now. And then I have a certain rate, a certain trapping rate. I multiply the trapping rate with the transition time over the fracture, and it tells me, okay, you have 20 trapping events, and for each trapping event, I choose a residence time from the distribution of residence time for this matrix block, for example. This can be an inverse Gaussian distribution if the matrix block is semi-infinite or whatever one can determine. But yes, in principle, this can be accommodated in this modeling framework.
Thank you. And no questions from the audience, but I do have some really practical questions. I see also Christine is just unmuting herself. Yeah. So Christine, if you do have a question.
Yeah, thank you for the great talk. I had one question. You are looking like mostly at the diffusion process in your model, right? But a lot of processes on pore scale also involve some interaction between fluid and the rock matrix. Is it possible somehow to include this kind of interactions in your model as well? And if so, are you planning to do this?
Christine, you think about reactions now?
Yes.
Yes, yeah. So this is something that we are working on, actually. So in principle, yes. So it can be also taken into account. Let's say very simple reactions. Let's say a very simple first order dissolution problem can be relatively straightforwardly integrated in this framework, no? Because one just has to assign a probability for particle to decay. But for more complex reactions, let's say bimolecular reactions, there are some approaches how to do this, but this type of things are still under development.
I see there's one other question coming from the audience, but I'm just going to sneak in my own question here. That comes from a really sort of practical side. So if you look at the subsurface reservoir, be it groundwater reservoir or something where we want to store CO2 or hydrogen, how would you use your framework to either predict the spreading of a contaminant plume, or possibly if you have measured some tracer distributions in the subsurface in some inverse modeling to learn something about the heterogeneity of your subsurface reservoir? So what I need to measure in a field application to drive your model as input for your model, either forward modeling or inverse modeling?
Yeah, no, this is a very good question. In principle, I say this exercise that we did here, we took as an input information of hydraulic conductivity. Yeah, I mean, if one has information on the hydraulic conductivity distribution, which one has at the mate site, because there are many let's say there are many sampling wells, it's highly experimented site. But I would say, in principle, if one let's say has a typical reservoir, we say, okay, I know more or less the structure, and this is this type of reservoir, I know what would be the hydraulic conductivity distribution. Then I could try to parameterize a forward model. In terms of doing something inverse, I would say looking at breakthrough curves of let's say for tracer experiments gives information, no? On the but the thing is, now when you look at breakthrough curve, you can do breakthrough curve. For example, you inject in a well and you subtract, or you can do a 2-well tracer test. One always has to have a little bit an idea of how the medium looks like and what are the processes that are occurring. Now, for example, in a fracture medium where I say, okay, I have hardly any interaction between fracture and matrix, and I look at a breakthrough curve like this, I say, wow, okay, good. So there is a lot of there's a very broad distribution of transport or of transport velocities. Oh, and this has to and this is related to a distribution of fracture apertures. So there I can make an inference at least at the heterogeneity of the discrete fracture network. And similarly, when I'm on the Darcy scale or when I'm on the pore scale, Darcy scale, I can make an inference on the distribution of velocities and on the hydraulic conductivities, and here in principle on the pore apertures, on the pore diameters. But as I say, one always has to have already an idea about the physical processes that are relevant. But then this is good now if I have an idea about the physical processes and I see a breakthrough curve, and then I see a behavior that is deviating from my paradigm. For example, if I would see here now something that would go out horizontally and go down, then this is not, I cannot accommodate this with a velocity heterogeneity. Then I would think, okay, there's a different process working, and in this case it would be matrix diffusion. So also a breakthrough curve can then tell me something about the processes that I need to take into account. Again, very long answer, but also, I mean, this is a very good question about how to parameterize the model and how to infer information. And I think there is also still a lot to be done.
Is Tanje Borg? I thought he's trying to relate some of the field tests, Tanguy, with doing the field side tests with a theoretical development. I thought there's some research.
Yes. Yes. But I mean, yes, there was this field tracer test in Plumeur, and there we used the continuous time random model to, let's say, to model the breakthrough curves. Let's say in principle to do a modeling based on hydraulic properties and medium properties, like for macro dispersion. Or macro dispersion, we have information on the mean conductivity or the effective conductivity. We need to know the mean hydraulic gradient, and we need to know the correlation length. With these three inputs, we can make a macro dispersion prediction. So here in this modeling framework, what we need the conductivity distribution. It's much more information, and we need also a characteristic length scale. But in principle, if it's possible to have some information of a distribution of hydraulic conductivity, then one can use this model to make a prediction.
The nice thing is if you have built your permeability conductivity distribution using some reservoir modeling software, you have that information, plus you have the length scale. You could even do a very quick steady state pressure solve to get the velocity distributions, correlations in the velocity.
Yeah, exactly. So this is what we did in this example here for the mate side.
There's one further question, again, comes from Arvind Kumar. He says, can you shed some light, please, on the connection of fluid stretching, mixing, and breakthrough curve spreading? You touched upon this a little bit in some of your explanations.
Wait. No, I mentioned it. Wait, about stretching? Wait, can you say it again? Stretching, mixing?
Can you shed light on the connection between fluid stretching and breakthrough curves? So fluid stretching / mixing and breakthrough curves / spreading.
Yeah. So okay. So the breakthrough curves that are showed here now, that you recover solute at a plane, then we talk about dispersion, or about let's say spreading of a plume. No? Also, we looked at purely advective transport here, so there's no mixing. No? So now, stretching and mixing, this is a totally different talk. I have to say. Also, fluid. I mean, what is mixing about now? So mixing in a heterogeneous flow field is about, first, the flow heterogeneity is deforming fluid elements that carry a solute. No, so they are stretched. So when I stretch a fluid element in one direction, I am basically making it thinner in the perpendicular direction because I have volume conservation, and I'm steepening concentration gradient. So now when I increase the concentration gradient, I get more diffusive mass transfer, and this means I get more dilution, I get more mixing. This is one effect of this effect, let's say, of stretching. Another effect of stretching is that I'm creating it's a lamellar type of structure of the, actually, let's go back to the initial example. I'm creating a lamellar structure. So here I'm creating lamellae, yeah, and that are folding back on each other, no? So this means on one hand, I get a stretching, I get dilution, which decreases concentration. On the other hand, I'm creating very long lamellae, which are folding back on each other. So I'm basically decreasing the distance between solute carrying fluid elements, so that the diffusion or local scale dispersion can act to homogenize them. Yeah? So this is about stretching, folding, and mixing. But this is a different. This would be a different talk. I hope this explained a little bit.
Certainly to me. Thank you much. I don't see any further questions coming through here from the audience. I think so. Our time is also slowly coming to an end. So I do hand over to Christine for some final closeout remarks. But first of all, again, thank you very much, Mark, for great talk. Thank you to the audience, especially Arvind, for the questions, and Christine for some final remarks. The next speaker. Over to you.
Yeah. Oh, sorry. Yeah, Marcus, thanks again for the very great talk. But now I would like to introduce our next week's speaker, which is Stéphane Zaleski from the Sorbonne University in France. And he will speak about dynamic contact lines and wetting. So until next week, as Hadi says, stay happy, healthy, and tuned into our Geoscience and Geoenergy channel. Bye-bye.
Thank you very much, everyone. Thank you. Thank you again, Marco. Bye-bye.
Bye.